If you've been following along with this series of lessons about chemical equations, we're just about done. One more small thing to add to our toolbox, and then a little more practice, and we'll be ready to go. We said that in double replacement reactions, the driving force is the formation of, which means you have to make a product that's a solid, water, or a gas. Okay? I haven't given you an example of one that forms water, but any acid-base reaction forms water. We'll do some practice with that today. But if it forms water, and an Arrhenius acid base, those reactions always form water, and that's your driving force. But I'm going to show you the one case that you need to know about in high school chemistry where a gas is formed, and it's really a reaction that occurs after the double replacement reaction. This is a two-part formulas here. We've got an ionic compound here and we have an acid here. So what happens is, if there's going to be a reaction, the first thing you're going to predict is that the front part of this is going to join up with the back part of that. The front part of this joins up with the back part of this. Right? Okay. So let's do that. We'll put Na and Br together. And then we're going to put the front part of this with the back part of this. Okay? And what I've taught you up to now is anytime this happens, the first thing you want to do is to figure out the physical states, because that's going to help you predict whether you have a reaction or not. Because if you don't form water, and we don't form water here, and you don't form a gas, and you don't form a solid, there's no driving force. But this is kind of an exception to that, and you have to watch out for it. So bromines are mostly aqueous. There are a few exceptions, but sodium is not one of the exceptions, so this is going to be aqueous.
Why didn't you put a 2 beside?
You don't put a 2 beside the Na because this subscript doesn't automatically transfer over. The only subscripts that automatically transfer over are those that are part of a polyatomic ion. So this just means there are 2 sodiums bonded to a carbonate. This subscript doesn't travel. This one is part of the polyatomic ion carbonate. It automatically travels over. You assume, at least initially when you're trying to predict products of a reaction, you assume that the polyatomic ions stay together. Okay? So this looks like it's going to be aqueous. Well, yeah, carbonates are mostly insoluble. The exception, I believe, group 1 is one of the exceptions, is it not? Is it not listed as group 1? Yep, group 1. Okay, so that looks like it's going to be aqueous. Here's the problem. Whenever you put hydrogen on a carbonate, something else happens after this. And so when you see this happen, you got to say, wait a minute, red flag. We got to go and move a little bit further forward. We have to balance this formula. Hydrogens are H+, carbonates are 2 negative. So this looks like it's aqueous, and indeed it is. But here's what happens afterwards. I haven't balanced the equation. I'm leaving some space to balance the equation. This H2CO3 immediately starts to decompose into water and CO2 gas. Okay? So we formed water and we formed CO2. We've got 2 kind of driving forces here, but you have to recognize that as a decomposition reaction when you see it. If hydrogen joins up with carbonate, that's what's going to happen. It decomposes. It automatically decomposes. That's just what this stuff does. Okay? Every time you open up a soft drink, this happens. Every time you open up a soft drink, this happens. This is where the carbon dioxide comes from. Inside your soft drink, as long as the cap's on it, under pressure, you've got mostly this. There's very little CO2 that's free, well, by comparison anyway. Not nearly as much CO2 that's actually dissolved per se in the liquid. Whenever you open up the top and you release the pressure, this decomposition reaction occurs automatically. Okay? Well, anytime you react baking soda and vinegar, baking soda is kind of like this. It's actually NaHCO3, and then vinegar has an acid, it's acetic acid. So the same kind of reaction occurs. You get 2 products. One's a salt and one's is carbonic acid, which automatically breaks down into CO2, and that's where you get the bubbling from when you react vinegar and baking soda together. But here's the tricky part, if it's tricky at all. whenever you see hydrogen joined up with carbonate, you got to automatically, as a product anyway, you got to automatically say, wait a minute, this is that red flag thing. I got to make sure I know that this is a decomposition that occurs. You have a question?
I figured it out.
Okay. Let's balance this equation, and then we're going to show how to put all this together. Okay, so here's our sodium, carbon, oxygen, hydrogen, and bromine. Almost didn't leave enough room. I'm seeing 2 sodiums here, 1 carbon, 3 oxygens, 1 hydrogen, 1 bromine. On the other side, I've got 1 sodium, 1 carbon, 3 oxygens, 2 hydrogens, and 1 bromine. Okay? I need to, we want to save oxygen for last, hydrogen next to last. We want to balance the sodium first, because that's the only other element here that's not balanced. To get that to balance, then I want to put a 2 in front of the species on the right that contains the sodium. That's going to change the number of sodiums and the bromines. And now we've got 2 sodiums and 2 bromines. Okay? And again, we're saving oxygen for last and hydrogen next to last. I'm going to go over here to this side and see that I've got 2 bromines on the right. I need to have 2 bromines on the left. So I'm going to put a 2 in front of the species that contains a bromine. Cancel out both of the elements that are in that formula. And multiply by 2. That gives me 2 hydrogens, 2 bromines. And that balances the equation. Okay? Alright. That hasn't changed the number of these carbonic acids over here. Okay? This is called carbonic acid because carbonates, whenever you make them into an acid, 8's become X, right? Carbonic acid. Okay? Alright. So this is not really the whole thing. What's really happening is this becomes this. So you really need to rewrite this equation to include that. Notice I balance this equation first, and then I'm going to go and show the decomposition as part of the same equation. What I'm simply doing is replacing this with these 2 things. And so that's actually the reaction that occurs. It's actually a little bit of both, to be honest with you. You still have some carbonic acid in there. But if you, the longer you leave the carbonic acid solution sitting out, the more of it decomposes. But there's always a little bit in there. In fact, right now, in any water in this room that's sitting open, there's carbon dioxide that's being absorbed by the water. And it's forming carbonic acid. But it's a reaction that you can only keep a certain amount of carbonic acid in there. Okay, only a very small amount stays dissolved. Later in the semester, we'll learn about equilibrium reactions, and it's an equilibrium reaction. If you take a straw and blow into a cup of water, you're going to acidify the water, because the more you blow in the water and pump that CO2 through the water, bubble that CO2 from your breath in the water, the more of this carbonic acid you make. So we can actually change the pH of the water just by breathing in it. Okay? Make sense? The more CO2 there is in the atmosphere, the more acidified the water becomes. Okay? You can measure the amount of CO2 in the atmosphere by how acidic the water is on the planet's surface. One of the problems with, the fact that we're putting CO2 into our atmosphere at a higher rate than we ever have in human history anyway, is that all the oceans and lakes are becoming acidified. And the theory is that acidified ocean then is breaking down the limestone that makes up our coral reefs. So theoretically, at least, the fear is that we're destroying coral reefs just because we put.
They always talk about that, but I never really.
There you go. Now you know. When you know the chemistry, all this other stuff starts to make sense. Okay, that makes sense. You got it? All right. Now let's do a complete ionic equation with this. Okay? In fact, you can do this. Why don't you do it ahead of me, and then I'll come back behind you and do it, okay? Remember, you're only going to break up those things that are acids or ionic compounds that are also aqueous. Nothing else breaks up but those. All right? You're doing a complete and net ionic equation. All right. Well, let's go through it then. This is an ionic compound, and it's aqueous, so this breaks up. Sodium ions separate from the carbonate. So we've got 2 sodiums, And because this compound is aqueous, the reason it's aqueous is because it's actually split up in the water and was sort of trapped by those water molecules. We have a unit later on where we'll learn about all that sort of thing a little bit more detail. Carbonate's 2 negative. We've got an acid here, and it's aqueous, so the acid is also one of those things that breaks up. We've got 2 hydrogen ions and 2 bromine ions, or bromide ions. Okay, on this side, this is aqueous and it's an ionic compound. It's a metal bonded with a nonmetal. We know that's a no, this is ionic because it has a polyatomic ion in it. We know this is ionic because it's a metal bonded with a nonmetal. And we've got 2 sodium ions. And we've got 2 bromine ions, or 2 bromide ions. Okay. Water is not considered ionic. It doesn't break up, so we're going to leave it as H2O. And this is a gas, so it's not going to break up. Okay? And there's the complete ionic equation. So what we need to do now is to go through and find those things that change and keep those. And just get rid of those things that don't change when we write this net ionic equation. So there's 2 sodium ions here on the left and 2 sodium ions on the right. We don't keep that for the net ionic equation. There's a carbonate ion here, but there's no carbonate ion on this side. So we're going to keep the carbonate ion. There's a hydrogen ion here, but no hydrogen ion on this side, so we're going to keep the hydrogen ion. Excuse me. There are 2 bromide ions on the left and 2 bromide ions on the left. It's 2 Br negative AQ, 2 Br negative AQ. They're exactly the same, so we're not going to keep that. Over here, what?
So if it's the same on both sides, you don't keep it?
If it's the same on both sides, we don't keep it. They're the spectators. They're sitting on the sidelines doing nothing. And it's what we call them, spectator ions. That's the name for them. Spectator ions. Okay? They're sitting around doing nothing. They're not really in the game here. And then we have, the only thing that we have over on this side that has changed is the water and the CO2. Okay, and there's your net ionic equation. We bonded 2 sodiums to 1 carbonate, so when we break all that apart, we have to break it apart into 2 sodiums. Think about it, I like to think about it like this, that when we're first balancing this formula, if I said, okay, write a balanced formula for sodium carbonate, we would write it like this. We'd say, all right, sodium. I know that's in group 1, so that's a 1 plus charge, right? And I know I have to memorize carbonates, one of my polyatomic ions that I have to memorize, and that's CO3, 2 negative. And I know that I need, because I have a 2 negative here and a 1 positive here, I need 2 of these to put it together into a balanced compound, a charge balanced compound, so it's neutral at the end, and get Na2CO3. Well, that's where we got it from right there, 2 sodiums, 1 carbonate. We're just undoing what we did to balance the formulas in the first place.
And also, on the complete, when do you not put the charge? Like I noticed you didn't for H2O or CO2.
Well, because those are covalent compounds that have been put together so there's no charge overall. We have an equal number of protons and electrons in these 2 forms here. This is the only one that you have to remember that's like that, so it shouldn't be hard, I hope, to remember that carbonic acid always decomposes into water and CO2, and those are covalent, there's no charge. Elements by themselves won't be listed with a charge, because remember, elements by themselves have no charge. This is not an element by itself in the original formula. What I mean is like when you're doing a single replacement reaction, and you have a metal by itself, okay? If in the original equation you had a metal by itself, or if you had hydrogen gas, or oxygen gas, or chlorine gas, those don't have any charge at all, because they're elements by themselves, or elements that are only bonded to themselves in the original equation, I guess, okay? Not the ionic equations. So what I have here is an ionic compound. I know it's ionic because I have a polyatomic ion here, sulfate. I know this is ionic because I've got a polyatomic ion here. Hydroxide. You were supposed to memorize a number of polyatomic ions, and those are the two, among the two you were supposed to memorize. So the first thing you're going to assume is that this is going to be double replacement. The front part of this compound goes with the back part of this one. The front part of this goes with the back part of this one. But initially, all we're going to do is just stick them together and not balance them, just so we can see if we have a driving force. With double replacement reactions, we have to find out what our products are before we can figure out our potential products, before we can figure out if we have a driving force. So we'll put aluminum with hydroxide. And I'm going to put potassium and sulfate together. Just sort of stick them together right now. I'm not balancing the formulas yet. All right, now hydroxides. Hydroxides are mostly insoluble. When you memorize the solubility rules, you should know that. There's some exceptions, but aluminum is not one of the exceptions. This is one of the insoluble parts of the solubility rules. It's on the bottom half, right? The bottom 4 rules. So these are mostly insoluble. There's some exceptions when you have hydroxide with ammonium and group 1, I believe it is. And so this is going to be a solid because there's not an exception to the insolubility of this hydroxide. Okay? Sulfates are mostly soluble. There are some exceptions, but potassium is not. Besides that, the very first rule in the solubility rules, under the soluble section at the top, says all group 1 salts, or group 1 ionic compounds, are soluble. So this is soluble for both reasons. So this is aqueous. Okay? Now we're ready to balance the formulas. Aluminum has a 3+ charge. It's in column 3A, I believe it is. It's called on the periodic table. Okay, let's look and see. 3A is correct. So it's right here, 3A. Okay, all these elements right here have a 3+ charge. Okay, when they're in a compound like this, binary and other compounds like this. And aluminum is always 3+. There's no exceptions for aluminum. Hydroxide is always 1 negative. That's one of those you're supposed to memorize. So to balance this formula, I need to have 3 hydroxides, and the only way to show 3 of them is to put a parenthesis around it and put the subscript 3 after that. Okay? Sulfate, the ion, has a 2 negative charge. Potassium has a 1+ charge. It's in column 1A, so it has a 1+ charge. To balance out this, to charge balance this compound, I need 2 potassiums. Okay? If you don't balance the formulas, balancing the equation isn't going to work out too well. So now we're going to write out all of our elements here. And we're going to do an atom inventory. Excuse me. I've got 2 aluminums. This 3 outside the parentheses means I have 3 times the 1 sulfur. I have 4 oxygens here times that 3. That's 12 plus 1 more over here. That's 13. I have 1 potassium and 1 hydrogen. Okay, on the other side of the equation, I've got 1 aluminum to start with. I've got 1 sulfur to start with. I've got 4 oxygens here, plus this 3 times 1, that's 3, plus that 4 is 7. I've got 2 potassiums, and I've got 3 hydrogens. Okay? And we're going to balance oxygen last and hydrogen next to last. So I want to find something else to balance first besides those 2. So I'll start with aluminum at the top. I've got 2 here. To give me 2 on this side, I'm going to put a 2 in front of the species containing the aluminum. Now that's going to change the aluminum count, the oxygen count, and the hydrogen count. So now I have 2 aluminums. Oxygens, I've got 3 times 1, that's 3. Times 2 is 6. Plus this 4 here, so right now I've got 10 oxygens. Okay? And let's see, hydrogens. I've got 3 times the 1 hydrogen here for 3, and then times that 2, that's 6 hydrogens. Okay, does that make sense so far? All right, now aluminum's balanced, sulfur's not balanced. Okay, I need to have 3 sulfurs on the right, so I'll put a coefficient 3 here. That's going to change the number of potassiums on that side, the number of sulfurs on that side, and the number of oxygens on that side. So that gives me, wait a minute, that's wrong, isn't it? No, that's right. To get 3 sulfurs, that's right. So I got 6 potassiums now. I've got 3 sulfurs now. And oxygens, I've got 3 times 1 is 3, times 2 is 6, and 3 times 4 is 12. That's 18 oxygens. Okay? Oh, I got the wrong one, sorry. Oxygens here, 18. And this is 6 potassiums. Okay, that's right. Now, let's see where we are now. All right, so we've got aluminum and sulfur balanced, but we've got to get the potassium balanced now, because we want to save oxygen and hydrogen last. To get 6 potassiums, I've got to put a 6 here. That changes the number of potassiums, oxygens, and hydrogens. So now I have 6 potassiums. I've got 4 times 3, or 12 oxygens there. 6 times 1 is 6. That's 18 oxygens on this side, right? Okay. And I've got 6 times 1, so that's 6 hydrogens. Hey, it's balanced out now. Finally, after all that. Whew. Okay? Now I'm giving you some tough ones, because if you do the tough ones now, if it's on the test, maybe it won't be quite so hard. All right? Got it? But this is the kind of thing you need atom inventories for, because imagine trying to do this without a way to keep it all organized. Okay? All right. Now we're going to write a complete ionic equation. This is aqueous, and it's an ionic compound. I know it's ionic because I've got this sulfate, a polyatomic ion. So I'm going to split this up. I've got 2 aluminum ions, and aluminum's a 3+, Al 3+, and I've got 2 of them. So this is aqueous. I've got 3 sulfates, all 2 negative, aqueous. Right? I've got 6 of these things, and that's 6 potassiums and 6 hydroxides. 1 of each in the formula times 6. 6 for each. 6 potassium ions, aqueous. Because this is an ionic compound, it's aqueous, this is going to be aqueous. Ionic compound, aqueous, the hydroxide is going to be aqueous. 6 hydroxide ions. Alright, now on the other side of the equation then, this is a solid. Solids aren't broken up when you write ionic equations. So this is just 2 Al, OH, parentheses, close, parentheses 3, solid. That's done. Now I need to break this one up. This is ionic, because I know I've got a polyatomic ion here. It's aqueous. It's going to break up. So I've got 2 potassiums in the formula times the 3. That's 6 potassiums. And it's aqueous because the compound that it started with was aqueous. And we've got 3 sulfates. Alright? Now we're just going to go through and only write down for the net ionic equation those things that are exactly the same, that change from one side to the other. So I've got aluminum here that's a 3+ charge, and it's aqueous, and over here it's not the same. This aluminum is not aqueous. Okay? It's not broken up. It's not an ion. So we're going to keep the aluminum on this side. 2 Al 3+, aqueous. And then sulfate, I've got 3 sulfate ions here, all exactly the same as this one. I'm not going to keep it. Potassium, 6 potassium ions, exactly the same over here. I'm not going to keep it. Hydroxides, I've got 6 hydroxide ions, but I don't have a separate set of 6 hydroxide ions that are aqueous over here. So we're going to keep the hydroxides. Okay? And so the only thing that has changed over here is this aluminum compound, aluminum hydroxide. Okay? And that's the complete ionic equation there and the net ionic equation here. Anytime you have a hydrocarbon, and it's a hydrocarbon because it contains carbon and hydrogen and nothing much else. It's a hydrocarbon, and you're combining that or reacting that with oxygen, you always assume that to be one of the simple combustion reactions we predict products for and balance equations for in here. Okay? And anytime that happens, your products are always the same. This is the easiest one to know the products of. It's always CO2 gas and H2O gas. Okay? Water's going to be a gas in this case because of the heat produced. Just to remind you, even though it's not part, we don't actually make it part of this equation in this class at this time, we're also producing light and heat. Combustion reactions always produce light and heat. Now we're ready to balance the equation. CH and O. I Probably didn't leave myself enough room over here because this is going to be kind of complex, I know. 8 carbons, 18 hydrogens, 2 oxygens. I've got 1, 2, and 3 carbons, hydrogens, oxygens on that side. All right, we're going to start by trying to get 8 carbons. Remember, we're saving oxygen for last, hydrogen for next to last. So to get 8 carbons over here, we need to put a coefficient 8 here. That's going to change the number of carbons and oxygens. So I've got 8 carbons. And the number of oxygens, 8 times 2 are 16, plus the 1 there. So right now I've got 17 oxygens. All right, got 18. We've got the carbon balanced. Oxygen we're going to save for last. Let's go to the hydrogen. 18 on the left, 2 on the right. To get 18 on the right, I need to multiply this species containing the hydrogen by 9, correct? That's going to change the number of hydrogens and oxygens. We're going to get 18 hydrogens, and the number of oxygens gets kind of complex. So 8 times 2 is 16, plus 9 times 1 is 9, and 16 and 9 is 25. So I've got 25 oxygens right now. Make sense? All right. When you have this situation, we've got an even number of oxygens on the left because of the O2, and an odd number on the right. The way you fix this is to go through the equation and multiply all the coefficients by 2 except the one in front of oxygen. So I'm going to change this to a 2, change this to a 16, change this to an 18. All right, that doubles everything over here except for the oxygen. So now I have 16 of these, and this I believe is, what is it, 36? Is that right?
Yes.
Okay. And then over here, I've got 16 carbons. I've got 18 times 2 is 36 hydrogens, and the oxygens I'm going to write down over here. I'm not going to try to save up on pencil lead here or pen ink. I'm going to write it down to keep up with it. 16 times 2 is 32. 18 times 1 is 18. And 1 is 10. Carry 1, that's 50, correct? All right. If I've got 50, that's an even number. I can fix the number of oxygens by simply putting a 25 right there. 25 times 2 is 50. A whole lot of balancing going on. Okay. But if you can do this, you can do anything. The only equations that have complete and net ionic equations, the only kind of equations that have ionic equations are double replacement and single replacement. This is combustion. It doesn't have ionic equations. You don't have to worry. There are some ionic equations for synthesis and decomposition. We're not going to worry about those in here, okay? Only double replacement and single replacement do you have to worry about those ionic equations. We have a we have a polyatomic ion here, so that's an ionic compound. We've got a polyatomic ion here. That's an acid actually because I got a hydrogen on the front. So if we're going to have a reaction at all, we're going to first look at this being a double replacement reaction. So potassium, we're going to join up with the perchlorate, KClO4. I'm not going to look at balancing it right now. I want to find out if I have a driving force first. H is going to go to CO3. I'm not going to balance it yet. I'm just going to see if it's going to give me a driving force. All right, now this is the one that I said a moment ago, earlier today. That's the red flag one. I mean, little bell should be going off in your head right now and say, oh, that's going to end up being the carbonic acid that's going to break down into water and CO2. This is the one that's going to break up. So even though initially this would seem to be aqueous, because carbonate ions are mostly insoluble except when they're bonded with group 1, we know that this, when everything's worked out, is going to break down into H2O and CO2. We're going to make a gas and we're going to make water. We're going to have a driving force because of this. Okay? Does that make sense? All right. So we want to go ahead and balance this. We know we need 2 hydrogens for that carbonate because carbonate's 2 negative. Potassium's 1 plus, perchlorate's 1 negative. That's balanced, and that's going to be aqueous because both of these kind of compounds are always aqueous on the solubility rules. CO3 is one of the polyatomic ions you have to memorize, and it's CO3 2 negative. And if it has a 2 negative charge, hydrogen always has a 1 plus charge in acids. So this is going to make it, you're going to need 2 of these to balance out the 2 negative on this. Now initially this looks aqueous, and in fact it is. Carbonic acid does dissolve in water. But we know that this becomes H2O and CO2. So what I'm going to do is I'm going to balance the equation first, then I'm going to rewrite the equation and break this up into CO2 and water. Okay? So let's see, we've got K, C, O, H, and Cl. 2 potassiums, 1 carbon. I've got 3 oxygens here and 4 here, that's 7. 1 hydrogen and 1 chlorine. On the other side, 1 potassium, 1 carbon, 4 and 3, that's 7 oxygens, 2 hydrogens, and 1 chlorine. Okay? Now we've got to get everything evened out. Oxygen last, hydrogen next to last. Let's start with potassium. I want to put a 2 here. That's going to change the number of potassiums, chlorines, and oxygens. So I've got 2 potassiums, I've got 2 chlorines, and 2 times 4 is 8, plus the 3 here. And right now, at least, I have 11 oxygens. There's oxygen 11, okay? All right, hydrogen next to last, oxygen last, going to go to chlorine next. I've got 2 on the right. To get 2 on the left, I put a 2 here. So that changes the number of hydrogens and chlorines and oxygens. I've got 2 hydrogens, 2 chlorines, 2 times 4 oxygens. Well, let's start with this one. This is 3 oxygens plus 2 times 4 is 8. That's 11 oxygens, and the equation's balanced. All right, I'm going to rewrite the equation now to break this up before I write the complete and net ionic equation. So K2CO3 aqueous plus 2HClO4 aqueous, then 2KClO4 aqueous, and this is the one I'm going to split up into H2O and CO2, and that's going to be a gas. Okay, H2O is a liquid, CO2 is a gas in this case. Okay, now we can write the complete net ionic equations. This is an ionic compound. We know that because there's a polyatomic ion here, and it's aqueous, so it splits up. 2 potassium ions that are aqueous. 1 carbonate ion that's aqueous. If this is aqueous, both these ions are aqueous. This is an acid. It breaks up. 2 hydrogen ions, and it starts out aqueous. It's going to be aqueous in the complete ionic equation. And 2 chlorates. This is ionic, and it's aqueous. We're going to break it up. 2 potassiums. 2 chlorates. This is a liquid. It doesn't break up. This is a gas. It doesn't break up. We're just going to rewrite those exactly as they appear. Please remember to write your L's here, lowercase L's, in the script form, because I can't tell print L's from capital I's or number 1s, okay? And then CO2, and write it as a gas, all right? Now we can write the net ionic equation, all right? Got 2 potassiums here and 2 potassiums here. They're the same. They're spectators. We're going to leave them alone. Carbonate. Here, I don't have a carbonate on this side, so I'm going to keep the carbonate. Okay. Hydrogen ions I have here. I don't have a hydrogen ion on this side. I'm going to keep the hydrogen ions. Okay. Chlorates. Got 2 chlorates here and 2 chlorates here. Okay, those are the same. I'm not going to mess with those because they're spectators. They're not changing. So the only thing left over here that is going to be left after we get rid of we leave off the potassiums and the chlorates is the water and the carbon dioxide. In order to figure out how to do this, you're simply going to recognize this is an ionic compound because it has a polyatomic ion. This is an acid, okay, and it has a hydrogen in the front, so it's an acid, except the exception to that is water, which sometimes is an acid, but most of the time we don't consider it that way. All right, so the front part of this then goes with the back part of this. Whenever you have an acid and an ionic compound, or 2 ionic compounds, or an acid and a base, or at least the kind of acid bases we deal with in here, you're always going to have, or predict you're going to have a double replacement reaction, at least initially. So the strontium is going to join up with this chlorate ion. Now I'm not going to balance the formula right now because I want to see if I have a driving force first. Then this hydrogen is going to join up with this OH. This subscript 2 is not part of the hydroxide ion. It doesn't travel. Okay, only the subscripts that are part of a polyatomic ion, like this 3 on the chlorate, travel automatically. So you take this H and put it with the OH. Ladies and gentlemen, it is going to break my heart, but someone is going to write this like this one on this test. They're going to do something like this, or they're going to do H and then OH 2, and that's not what you do. Okay, this is wrong.
I think I know why this
All right,
I can see the subscript on the OH.
it's not right. Don't do that. Okay. Okay. Now look. Now we're ready to balance. Now we're ready to figure out if I have a driving force and the formation of water. Yes, I didn't write it H2O, but it's still water. It's HHO, 2 H's. Okay. This is a liquid. In an acid-base reaction, we'll show it as a liquid. All right. Then we got to figure out the physical state of this. And chlorate is one of those polyatomic ions you're supposed to have memorized. It's on your solubility rules, which you're supposed to memorize. And all chlorate compounds are always soluble, no exceptions. It has a 1 negative charge. Strontium has a 2 plus charge. And to charge balance this compound, I need to have 2 chlorates. And since it's always aqueous, we're just going to write aqueous, always soluble. Okay? Now that we've got the formulas properly balanced, we can balance the equation. SrOHCl. And so we've got 1 strontium. I have 2 times 1 oxygens here, plus this 3, that's 5 oxygens. I have 2 hydrogens here. 2 times 1 is 2, plus this one I have 3 hydrogens. I have 1 chlorine over here. On the other side, I've got 1 strontium. I've got 2 times 3 oxygens here, 2 times the 3 here. That's 6 plus the 1, that's 7 oxygens here. I have 2 hydrogens, and I've got 2 times the 1 chlorine in the chlorate formula, polyatomic ion chlorate. 2 times 1 is 2. Now remember, we're going to balance the oxygens last and the hydrogens next to last, so we want to start with the chlorines. Since I have 2 on the right and have only 1 on the left, I need to put a coefficient 2, in front of the species that contains the chlorine. You can't mess with the formulas once they're balanced. Okay? So put a 2 here. That's going to change the number of hydrogens and chlorines and oxygens. All right. So that gives me 2 hydrogens. The number of oxygens, I have 2 times 3, that's 6, plus this 2 times 1, so 6 plus 2 is 8 oxygen. Oh, I forgot the 2, 2 hydrogens here and 2 here is 4. Okay, now, so I've got strontium balanced and chlorine balanced. Now we're ready to go to the hydrogen. All right, so to get the hydrogens balanced, I need 4 on this side, and I'll put a coefficient 2 in front of the water to give me 4. That's going to change the number of hydrogens and oxygens, and that'll give me 4 hydrogens and 8 oxygens. 3 times 2 is 6, plus the 2 times 1, 6 plus 2 is 8. Okay? Now that's a balanced formula now. Got a balanced equation and balanced formulas. Now we're ready to write the net, well, complete ionic equation first, then net. This is an ionic compound. It's aqueous, so we're going to split it up. We have 1 strontium. Strontium has a 2 plus charge. This compound is aqueous because they split up. So this ion is aqueous. We've got 2 hydroxides in this formula. So we're going to have 2 hydroxides separated as ions. This acid is aqueous. It's going to split up. We've got 2 hydrogen ions. And since I have 2 of these formulas, I've got 2 chloride ions. Strontium chloride over here, I've got, this is aqueous, it's an ionic compound, it's going to split up. Strontium is 2 plus, I have 1 of those. I have 2 chlorates. This 2 outside the parentheses means I have 2 of these things inside. is not aqueous. Water is not ionic or an acid, although rarely we treat it like an acid. But as far as these kind of equations are concerned, this is just going to stay just the way it looks here. So this is going to be plus 2HOH liquid. Okay, and there's the complete ionic equation. And then to write the net ionic equation, we only keep the things that change. Everything that doesn't change, we're going to leave out. Because if it doesn't change, it's not in the game. It's a spectator. It's a spectator ion. That's what we call it. So strontium is the same on both sides. We're not going to keep it. Okay? We're going to drop it like they dropped Steve Smith from the Panthers. OH negative. That's going to be dated in about 2 years when people watch this video. They won't know who Steve Smith was. Steve Smith was a longtime Panther and got dropped. Okay. Big news in sports yesterday. Okay, here we go. Here's the OH ion, but it's not an OH ion over here. We're going to keep it. It changed. Okay, hydrogen ions. There's no hydrogen ions over here. They're bonded in this water molecule, so we're going to keep the hydrogen ions. Chloride ions, exactly the same on both sides. 2ClO3 negative aqueous. 2ClO3 negative aqueous. We're not going to keep those. Those are spectators. Okay, over here, the only thing that we're going to keep is the water, or the two waters actually. And there's your net ionic equation. And the driving force is the formation of water in this case.